Thank you very much for that introduction. Oh, and now I got a little bit of technology to play with. So before I actually start, I want to thank you guys for having me out here, and an unexpected treat happened. One of my earliest memories as growing up is about 5 or 6. My father was working on a PhD in agriculture looking at the effects of fertilizer on wheat. And so one of my earliest memories is sitting around a little vinyl table trying to thresh wheat and count the number of heads that are in it. So this whole idea of agriculture here on Earth and doing that now in space goes much deeper than I had actually realized until I was walking around Grand Farms here. So thank you very much. So I am a scientist. I'm a plant biologist. I do consulting on indoor agriculture. And my objectives today is one. I want to convince you that the idea of growing plants in space to keep people alive on missions to Moon and Mars has relevance to us and that application of feeding the people on Earth and how we will do that the next 3 billion people. You know, that's a lot, supposedly coming in the next 25 years. That's the population, I'm going to lay down my wheat, the population of North America, South America, Europe, Australia, Japan, and part of North Africa are all going to be coming to dinner. And we're setting the table now. So what we need to be doing is understanding how we can use all of our assets, all of our technology to use the imagination for that innovation and then ultimately that implementation to solve our exploration to Moon and Mars and apply that here on Earth. I'm supposed to point this. Why am I not moving? Next slide. There we go. Okay. So the name of my company, Synergy, comes from a series of 3 experiments that I performed on the International Space Station. And those were biologically looking at the beneficial effects of mutualisms between plants and microbes. And in microgravity, are they able to find each other? Do you have these chemical signals? Are they able to go from point A to point B? How do we know that we're friend or foe? Do those signals change in the absence of gravity, of these various gradients? Can they actually, all of the environment changes. So we did a series of experiments, and then we brought those organisms back and grew them out. And what we have discovered is many of those still have increased activity, bioactivity, that is beneficial in promoting their biostimulants to promote plant growth. And we're in the process now of verifying that we can use that in the fields, that we can actually have that application of using microgravity and our understanding to accelerate the discovery of new organisms that have those characteristics on Earth that have application. But I don't want to talk too much about that because, well, we could be here all afternoon because I love it. But what I do want to go back is go back in time of what actually brought me into space agriculture. Like I said, my earliest memory, one of my earliest memories is sitting on a table counting seeds of wheat for my father, trying to figure out, you know, the effects of fertilizer. I ultimately got a degree in horticulture. I got a PhD in pomology and was teaching horticulture, apple, peaches, plums, and pears at the University of Maryland. And then the opportunity came down to go visit a site at Kennedy Space Center, Florida, working on a project called CELS, Controlled Ecological Life Support Systems. Its mission was beautifully simple. Demonstrate the feasibility of using biological life support, that's plants and microbes, to regenerate the atmosphere, purify water, and produce food on a 1-person scale for 1 year on a sustainable basis. For a plant physiologist and horticulturist, that was like walking into plant physiology Legoland. Who could say no, you know? All these toys to play with. Well, that went on for about a decade, is incredibly productive, over 600 papers and publications and students. I won't go through all of those. But what I will share with you are what I think our really, really big impact was. We completely redefined the limits of productivity of the field crops by able to control the nutrients, the light, the CO2, the temperature, and recycling and reutilizing. At the times of the day, we were told we couldn't grow potatoes without dirt. We went hydroponically and produced twice world record field yields in 2/3 of the time. At the day, that was early 90s, we were 4 times field yields. We're probably twice the field yields of some of these varieties that I've seen that developed in the past 2 decades. What we were able to do to lettuce was 20% higher than any other reported models. Those standards are now used for every indoor production model that is used worldwide. So what we established, not through new genetics, not through new understandings of genes, not through selections, but basic horticulture and application of physiology, those limits of production. So that was super exciting for us. And we started doing lots of calculations on how big a thing we'd need on Mars, and I kind of think Mark Quatney might have seen all of our potatoes. They won our yield derbies. But what the next thing, what we were doing is not acceptable to grow in space, because we have to have light. And that light is coming from high fluorescent lights and high pressure sodium lights, which we could grow really good plants on, but let's think about it. They get really hot. You can't touch it. They break, you've got to clean it up, and if you're in space, I'm sure we'll hear about in just a few minutes, you don't want a bunch of broken glass floating around going in your eye and up your nose. So the safety hazards, the longevity, the resupply said we need another source of light. And that led to the utilization of LED lighting. And NASA funded a series of experiments over a very long time on establishing, identifying, and improving technology for LED lighting that has a huge benefit, not only in making it possible to grow plants in closed environments very close, but to have longevity and safety. So what's been the outcome of that? Well, after all of that kind of work, which, there we go, that currently on the space station, almost for the past 5 years, astronauts have been growing their own food. They've been growing lettuce, peppers, bok choy, various salads, crops, learning how to grow, eat, and water those in space. They are utilizing that to supplement the chemical constituents, not so much for the calories that keep you alive, but for the phytochemicals that keep you healthy, psychologically fit, and resistance to disease, and as a countermeasure to radiation that can be exposed on long-duration space missions. But that's not the only real impact. From my view, the real impact that has happened, that those 2 technologies, finding the absolute limits of productivity by controlled environments, and then the technology to allow that to happen in a closed space, has allowed the emergence of a new industry in agriculture, a new sector of vertical farming, of indoor farming, that has productivities on a per acre or per hectare or per foot basis greater than anything that's been achieved in the history of mankind. And that was not possible before these innovations of the limits of technology, finding the technology that allowed that to happen, and then the inspiration and financing to show that at scale. That is changing the way food is being produced around the world. What's happening a little bit closer to home? Just up the road, there's NASA-funded research at the University of North Dakota. You'll, I'm sure, hear a little more about that later today. But the idea is, if you're going to go to Mars, we're going to colonize it. Let's use the resources that's there. Let's take that frontier spirit of we're going to go, live off the land. We've got to be sustainable. We've got to innovate. We've got to use imagination. So what do we have? We have a lot of soils. Those soils have nutrients in them. We should be able to use those for fertilizer. But it turns out that the Martian soil, unlike what was happening in the movie The Martian, is covered with a bunch of toxic materials. If you put something in it, it's going to die. And you can wash that out with water, more or less. So let's say you get past that. Then you have all of these elements that are almost like dust, but they're rock dust, and the nutrients are inaccessible. How do you make that accessible? Well, the idea is we will biologically process, and we're using worms to accelerate the weathering. So the waste material from the food that is eaten, the packaging that is in, the plastics, all of the organic material that's tossed out as waste, that's either sent to be tossed in a crater to be there forever, is now being fed to worms. And within that, we're putting in the regolith. And as it's biologically being processed through the gut of that worm, it frees up that nutrients. So what has the results been? We have tried to grow plants in regolith in many different ways, and nothing grows. We might get them to germinate, then they die. They don't germinate, or they germinate and they die. We process these biologically in lots of different ways, and they grow. We have managed to demonstrate a biological technique to take a toxic soil and make it productive. We're not to where we have Miracle Grow and slow release fertilizer in it, but we're 75% there. So we are making progress. I think we can all imagine the applications of this as degraded soils, marginal soils that can now be reduced to feed the 3 billion people that are going to come to Earth. Now, my mission is, when I left Kennedy Space Center, I didn't leave Kennedy Space Center, I'm still at the gate of it, but I left working at Kennedy Space Center about 5 years ago, specifically for the goal of taking the lessons and opportunities that you get from learning to grow plants in space and applying them to solve the solutions here on Earth. And that's not because it's entirely my jollies, although it does get me off and I enjoy it a lot, but it is ultimately for the generation that's coming. The 3 billion people that we are going to have to feed, these are their problems. We need to excite them on that this is a problem that needs done, it needs solved, and this conference, I really appreciate being here because it's pulled together some of those opportunities and a direct access to the funding that will allow that to happen. That perceived distance between growing plants in space and producing food down in the dirt is a lot closer than we think. And so as we bring those concepts together, we have that opportunity to change not only our lives, but those that are coming. So thank you very much for the opportunity to be here, to speak and follow up, and thank you for not running me off the stage.